Just in a few words, what we did last time. We considered something which we called multiplicative random processes, in which essentially we have an iterative procedure by which we updated our variables w of t, where w was essentially, we were imagining as the position of some random jumper on a real axis. So it was jumping either to half of the distance w or to double the distance w. And with the condition that if he got to 1, then one would not get to half, but rather stay there for that particular time. And maybe next time would be multiplied by 2 and get to 2. So the possible values for w would be 1 or 2 or 4 or 8, and it would jump between those values. And we imagined that we had many realizations of this process. So we could speak about how many such random jumpers would exist at each value w. How many at 1, and how many at 2, and how many at 4. And we asked what would be if I wait enough time, whether there would be some configuration, some numbers of w, which after I reach this particular numbers, there will be no significant change in the system, that these numbers will be stationary. And we found essentially that there is such a distribution. And of course, the overall factor doesn't matter. If I just take twice as many in each position, then they would still be stationary. So we could normalize either by saying that we know how much is n of 1, or as we will do in the next in this lecture, we'll normalize by asking that the sum of these numbers will be 1. So we speak in terms of probabilities, in terms of what is a fraction of representations out of the entire, which we call 1, which is at a given time at w equal 1, what is a fraction at w equal 8, and so on. So we can have either the normalization by just taking an overall factor, or by taking the sum of all of them and divide it by the sum, and then we have a bunch of numbers whose sum is 1. So this would be a probability. And the important thing is that we got that whatever is the number w here, the number of realizations which are at that particular number is proportional to w to the minus 2. And we call it power law. In general, one doesn't have to have lambda equal to so in general, one has a random number here, lambda, multiplying w of t in order to get w of t plus 1. But lambda doesn't have to be 1 over 2 and 2. It could be 1 over m or m. And in fact, it can be in general, as we'll see, almost anything. I'm just taking just two possibilities, because this allows me to make the computations very, very simple without integrals and differentials and nothing like that. So a more general situation would be that I multiplied with m or 1 over m, and that the relative probability between them would be a factor of k. And in this case, one can repeat the rather simple procedure which we applied to obtain this result. And we obtain the result that n of w, where w can take values of the type m to the n, in the same way in which only was allowed to take powers of 2. Here it is allowed to take only powers of m, because we multiply or divide only by m. And the stationary distribution of how many of the realization of the process have a particular W will go like k to the minus n, where k is this probability. And again, the normalization here is in terms of the first one, but in a short while I will normalize such that the sum of the n's is 1, and therefore they are essentially probabilities. They are what is the fraction of realizations of the process are in each value of W. I remind you also the way we got it. We got this relation. We said that if we want that the flow from this side to this side would be equal to the flow from this side to this side, and given the fact that the ones which go to the right are a fraction 1 over k from the ones which go to the left, then it means that in order to have this equal to that, I have to have this k times this. So 1 over k times this would be then 1 times this. So this is a very, we did a much more detailed computation, but that was one way to see that the ratios between the height, the number of n of W at different sides, at different powers of m. This is m to the 0, m to the 1. For some reason it doesn't appear, right? Will be they will be in the ratio of k to the minus n. And moreover, we can, if we call k, if we just parameterize k as a power of m, k equal m to the q, which again, it's just a definition that q is the logarithm of k over logarithm of m, or logarithm of k in the basis m. But again, we don't have to use this definition of the logarithm. The important thing is that if we parameterize k in this way, then we are getting that n of W is equal to, it's proportional to n of 0 times W to the minus q, because essentially k from here is m to the q. Together they are m to the minus qn, but this is equal to m to the n to the minus q, and m to the n is W, and therefore is W to the minus q, and this is how we got it. Last time I jumped some of these trivial steps, and we lost some minutes to clarify this. I hope that now it is clear. Is it? Is it clear how?
Well, do we really have to understand that whole middle step, or can we just use the final?
The answer is that one of the parts of the ethos of physicists and other scientists in these formal sciences is that understanding is much more important than remembering. It's part of the ethos. So even if in principle you can get by not understanding it, and I have in my own family some of the members that they studied things, and they didn't, they just were interested of what is the final formula and to apply it. I would rather make an effort myself too, and together with you, that we do understand how. Well, okay. Do you remember that we got this formula?
It's for a multiplicative.
Yes, yes. So this one you accept that we deduced it. Yes, it's for this slide it's given, and now I'm calling m to the n W. Okay. I'm just giving a name to it, and I'm calling k m to the q. It's always possible to find a q such that k will be m to the q. Okay, this is a definition of q.
That's arbitrary.
That's also a definition of q. And I'm plugging both these definitions here. Here I'm writing n of w, and here I'm writing in place of k to the n, m to the q to the minus n. But now I'm using the fact that something raised to a power raised to another power, it is the product of the powers. And therefore, this is equal to m to the minus nq.
Could you say that again? Something raised to the powers and product?
Okay. So this, let me put it this way. This you can know by heart, what I'm writing now. Now I'm writing something that you have my moral permission to know it by heart. M to the q to the minus n is equal to m to the minus qn. Okay? And because of this, it is also true that it's m to the n to the minus q. So the point is that whenever I have a power to another power, it's that number to the product of the powers. Okay? This you are allowed to remember just by heart. Which indeed puts the philosophical question of if you come to learn by heart anyway something, why is this and not that? And the answer is that this relation is much more general. You can apply now to very many other conditions, while this one is just a particular statement about power laws, the properties of power. Okay. So now is it clear?
Yeah, but I don't know what we got out of making it into that equation.
Well, you got that now. You see that this has the form of power. W to some power. Now, this is important because, as I said, in the previous case, we had something which was essentially some number to the, which I don't remember what it was, let's call it A, to the power minus W. So it was going, the W appeared in the exponential. This was an exponential. And this is a function which goes down very fast. This is a function which could go down much slower. Now, this is important. I mean, mathematics, as you see, so from time to time I consider it important for some reasons, education. But the really important thing is that this kind of behavior, in which the W appears to the exponent, characterizes the kind of physical systems like the energy of the molecules in this room, which are very uneventful. Nothing really happens macroscopically with the air in this room unless there is a storm or something. On the other hand, this thing here allows, if you plug the numbers in, and we did it essentially, if you put something like 10 billion people, 10 billion realizations here, then you will get some of them which are very, very outstanding. They have $100 billion, and they become very important for the entire system. So having this formula or this formula, it makes a hell of a difference. And this is something which, again, I would like you to remember. Again, it's as much as I was claiming before that we don't like to remember something. This, of course, we do remember. We do remember that these two regimes, one of them coming from an additive process, like the molecules gaining some quanta of energy and losing, and one of them coming from a multiplicative process, like something gaining 5% in one day, or somebody losing 10% in some other day. These two processes leads to very different things, to either processes like the air in this room, in which nothing really macroscopically important happens, or to the kind of economic systems in which you have very rich people, you have very large, you will see in a while that we have very large fluctuations, not like the fluctuations in this room, which are essentially negligible in terms of the temperature So I hope that now I brought you into the frame of mind closer to the one in which I am when I speak about these systems. And now I remind you how we showed it graphically. First of all, we took what we call the double logarithmic scale, which now you understand. In place of showing the 10 to the minus 2 and the difference between 10 to the minus 2 and 10 to the minus 3, it's 10 times larger than between 10 to the minus 3 and 10 to the minus 4. And still here I'm showing equally because because I want to have a more general view. You see, if I would plot the energies of the molecules, because they are all of them more or less of the same size, I can put them on the same graph and maybe see all of them. But if I look at the wealth of people, then if I am considering some only the scale on which only the big ones appear, then the small ones would not appear at all, even though there are very many. So we have this double logarithmic scale in which what we are plotting at equal distances are the powers of some number, either of 2 or of 10. And then we can represent the process of multiplication by having, and this time I'm taking the multiplication not just by 2 or 1 over 2, but by relatively random numbers. So I start with everybody at 1, 10 to the 0, and then after some time, after they start to, some of them they go to the left and some of them to the right, and they start forming a shape, which in fact a parabola shape on such a double logarithmic scale corresponds to the Gaussian distribution. We'll discuss a little bit more about what is Gaussian distribution. It's a normal distribution. It's worth remembering too, because it appears in almost any statistics which economists or social scientists are doing. And at some stage, what happens is that when this lower bound enters into effect, the point at which I'm not allowing anymore the representations of the process to go to lower values than that, in this particular case, it's probably 0.2 or 0.3. Then the entire population aligns itself on a straight line.
I don't get all these different lines.
Well, these are in time, okay? So in time, I started with everybody having the same value of W. This is the W axis, and this is how many of them.
Meaning the amount of money?
Yes. This is how much money they have, and this is how many they have this amount of money. So now nobody has 10, nobody has something else, everybody has 1 on this, let's say 1,000 or 100, 1 unit. And so it starts like this. Now, this is how I start the process. Why do I start at this? Because my point is that no matter with what I start, the stationary distribution, the one which I computed, that if I get to that, it doesn't change anymore, it will be the same. So I'm making the point that even if everybody starts with the same wealth, and even if everybody gains or loses in a random way, in a potentially equal way, the same probability for everybody to gain a factor or to lose a factor, then I get, of course, this. Now, I told too many words. The point is not whether it's Gaussian or not. The point is that now you have, for different values of wealth, you have different values of how many realizations of the process, how many people have it. And at the beginning, you have this, that they still remember there are very many which are still at the old value because they lost, but then they gained again, so they are at this value. But some of them, they were systematically more lucky or systematically less lucky, and I get this shape.
And what's that?
This is the social security. This is the part that I said that nobody can go less than a certain value.
The lower bound.
Yes, the lower bound. So, so as long as they don't get to the lower bound, then this whole thing is symmetric and nice. And once they get to the lower bound, then the guys which are at the lower bound, they start accumulating there. So the shape of this distribution of how many have different wells starts being changed. And you start having very many which are poor, and but you start having some of them which are orders of magnitude less. You see, this is 10 to the minus, more than 10 to the minus 2. This is 10 to the minus 6. So we are speaking about 1 in 10,000 has 1.5 orders of magnitude more than the others. Or if you want, has 1 order of magnitude more than the average, because of course the average will stay the same.
So the change that happened over time because of the lower.
Exactly. And eventually, if I keep running, then this line, in a sense you can say miraculously, starts behaving like a very straight line. Well, it's not miraculously, because you remember that power law, when we express it in terms of when you take equal exponents at equal distances, it is a straight line. This we showed before, but I can remind you even now. You see, if what I do is put on the x-axis this n here, it's the exponent. Okay, suppose that m is 10 and k is 10. Okay. Okay, I give you an example, because it's a graph which I showed to you. If m is 10 and k is 10, and if I show on the y-axis just this n, not m to the n, but n itself. N parameterizes the value of w, of the wells, but in terms of the exponent, not in terms of the number itself.
I thought that was what q did.
Hmm? First of all, it might be that I changed the conventions, and maybe, but from what I remember, q was on this side, was essentially what I call 1 over k. K to the minus n, it was q to the n. So let me write it aside such that I can, such that I can compare with this. So this one, this is W, okay? It's m to the n. And this is k to the minus n, okay? So I had that the probability or the frequency of W being equal to m to the n is proportional to k to the minus n. Okay? So look here what happens. If I take m equal to 10 and k equal to 10 there, then what I have here is essentially the n's. This is how I defined it. You see, it's 10, this is m, and it's 10 to the minus 2, 10 to the minus 3, this is the n.
So
to
what
it,
is the exponent?
so, yeah, so this line, having a straight line like this, it means exactly this, that whatever appears here appears also here, the same exponent. Because this is how I'm plotting. I'm plotting, formally I'm plotting this thing, which is W, and I'm plotting P of W, which is this guy, but I'm plotting it on a scale such that what appears here, it is k to the minus n, but it is actually the different powers of n are at equal distances. So it's n. And what appears here, because W is m to the n, and I put the different powers of m. So this is m equal m0, m1, m2, m3. But they are the distances of 0, 1, 2, 3. And these ones are also the distances minus k to the minus 1, k to the minus, minus 2, and so on. Okay? So what I have...
So K is probability?
Excuse me?
K
is the probability or proportional to the probability. Yes. It's the frequency of that thing. So it depends how I normalize it. But you definitely can think in terms of probability. So if I put the probability on such a scale in which what it counts are the exponents, and I put the wealth on such a scale, then I get a straight line. If my dependence is of this type, which means if it is of a power law, because I established just at the beginning of this lecture that this is equivalent to the to a power law, to W to the. So these are simulations. What I told you, the same story. It's now all of them on the same graph for different times. For this was for t equals 0. This is for t equal 10 time steps. This is 100 steps. This is 5,000 steps.
What do you mean steps?
Well, steps is, you remember, my entire process is W of t plus 1 equals something, lambda or whatever I called it, this number here, W of t. So each time that I go from t to t plus 1, I call it a step. And if I do it for very many realizations, then I get this graph for their distribution. Okay? So at the beginning, I start with something which is not the stationary distribution, but I always end up with the stationary distribution, which looks like a straight line on a double logarithmic scale.
What if each person were to start with a different amount of money?
That's the point. This I'm not going to show, but in this particular case, they will still end up with exactly the same final thing. It's not in every process like this, but in this particular process and in many others, not only that you have a stationary distribution, but no matter with what you start initially, you end up with that stationary distribution. So as I showed to you maybe from the first lecture, not only that you do get in simulations this kind of, this is a real simulation done the way I told you. Not only you get this perfect fit of having a straight line on a double logarithmic scale or a scale in which different powers are at equal distances, but in fact, they correspond to what happens with the real wealth in different countries, in different times, in reality. I think that this was just from Sweden in the 60s, but I showed to you in a previous lecture even quite a number of graphs from the United States in the last 20 years. And they are all of them looking like this. This is a simulation, and these are the measurements. So now the problem with once we want to make the contact with the measurements, the following problem appears. In order to obtain these results, we assumed that the probability of losing, the probability of going to the left, was larger than the probability to go to the right. Yes, you remember? Otherwise, I wouldn't get that.
Because of the lower bound?
The lower bound was helping me then to construct it. But if I wouldn't have that this one, the probability of these guys to go to this is larger than the probability of the red guys, then I wouldn't have the fact that this one is larger than this one. Everybody would, then I would, if I have this probability larger to go from left to the right, then everybody would go to the right. You see, the lower bound will not be important anymore. Suppose that I don't have anybody going to the left. Everybody goes to the right. Then there is no reason for these guys to accumulate here. They will just go on. But this is actually what happened in reality. People are playing in the stock market, let's say, in order to gain. If they are told, look, why don't you put your money in a place which is all the time predominantly losing, they wouldn't do that. And in fact, it doesn't happen. And in other applications in which instead of wealth of people and people, you can have cities and their population. And again, the population of cities is fluctuates proportional to how big they are. So a city of 1 million has a probability to go to 1,100,000, and a city of 1,000 would go from 1,000 to 1,100. But with
population size?
Yes. So it's the same, as I emphasize, this kind of multiplicative process is extremely general. There are tens and hundreds of What?
How is population size multiplied?
Well, imagine how many people are. Suppose that you put you take some statistics of people, and you in the central bus station of Tel Aviv, and you ask them how many people go to. Give me a small place. A small city, Afula, and how many they go to Jerusalem, then you would accept that it would not be an equal number. It would be much more to Jerusalem because Jerusalem is bigger. So now it's an example of people just going occasionally to Jerusalem. And now we are speaking about people really moving to Jerusalem. But moving to Jerusalem, or there are very many people moving to Jerusalem, and of course very many people moving out of Jerusalem, and they are proportional with how big is Jerusalem. And the ones which are going to in and out of Afula, they are proportional. Their number is proportional with how big is Afula. Okay, so this multiplicative process is true for very many realizations. Or if you want the population of certain animals, how many cats are born in Jerusalem and how many they get out of Jerusalem or die? There are very many. In some smaller town, you will have less cats. Maybe it's the same density of cats, but less cats being born. And so you see, no wonder that the population of cities, or the number of cats, or the wealth of people, or very many other examples, they do have this law. And this is why I'm actually spending so much, so intensive effort to transmit it to you, because I know for sure that it will be relevant to almost any, without knowing your fields of interest. I know it's true for any field of interest, in particular for the number of times that a particular word appears in a text. That was one of the first applications of power laws.
But I just don't understand why it's like multiplicative and not additive.
Multiplicative, it means that the changes are proportional to how much you have already. And I just proved to you that for Jerusalem, the change is proportional to Jerusalem. You also have, like in the case of words, one way to think about it is that if you have used the word in a certain text, then the probability that you will use it again, it's much more probable. I don't know, if you take my Michael of Amos Oz, then once he gave the name Michael to one of the main guys, then you know for sure it will appear a hell of a lot of times, as opposed to, let's say, Zarathustra, which probably doesn't appear at all in that place. But it would appear a lot of times in Nietzsche's work, okay? So you have this kind of situation in which you have, if something, sometimes this effect is called, annoyingly, of course, rich get richer, which is unfortunately, as you see, kind of true, but not always. It's still, there is this random process. Okay. So we had these things, and now as I said, now I want to generalize the process in such a way that I will get it even if I do not assume that people are losing all the time, or that the cities are losing population all the time. So I want to have a situation in which this multiplicative factor is not necessarily more probable to be less than 1 than to be more than 1. Of course, in this case, I have the problem that, as I said, the lower bound becomes irrelevant, because if everybody goes to the right, then having a barrier to the left would not affect anything, and I would just get this kind of flattening distribution, which I have shown it in some of the previous lectures. So the idea is to actually have to have a lower bound which goes together with the distribution itself. So I'm saying, okay, I'm taking these random numbers such that, in fact, they are moving the W's typically to the right. Not absolutely. I can leave some probability for going to the left, for being less than 1. But typically, they would grow in average. And then how can I still do such that the system will still have a power law? And the idea is the following. I'm saying, each time that some of these guys is getting smaller than some fraction of the average, I call this W without an index, it's the average of all the Wi's at that particular time. And I go to each I and I update it from time to time in a random way. And now I multiply with eta. And I'm saying some of the etas will be small, or maybe they are not so small, but they are small compared with all what everybody else has been multiplied lately. And because of this, I can get a Wi which is less than this fixed fraction C of the average. And I'm saying, if this happens, I'm going not to allow this to get below that value. I'm just putting it by hand to the value C times the average. Okay? So I'm doing exactly the same thing what I was doing with the fixed lower bound, except that now the lower bound is fixed by connecting it to the average of everybody else. Of course, this is exactly what Social Security does, because if they would have fixed some amount in 48 when they established the state, and they would keep giving that, I don't know, maybe they had half of a lira, and they would give the equivalent now, it would not help anybody. If you really want to have relevant Social Security, you have to have exactly this kind of thing. And it's even maybe I will, after I make enough mathematics, which I want to make with you, then I will also explain to you why this C, it's almost the same in different countries, in the Western countries. Like in Israel, in the United States, it's something between 1/4 and 1/3, which is quite a lot if you think about it. You ensure that nobody has less than 1/3 or 1/4 of the average, which is not negligible. So if you do that, then the situation becomes not so bad, because now you can do the following trick, so to speak. I'm going to say, you know what? I'm not going to speak anymore about the Wi's, because the Wi's, they are all of them moving and changing. I'm going to speak about the normalized values. I call them xi, which are Wi divided by the average. Now those things, they have a chance to be stationary. The other one, they cannot be stationary. They are all of them going to larger and larger values. Maybe not to larger real wealth, but at least to larger nominal wealth. So, but xi definitely cannot run away, because in fact, if you take the average of the xi's, can somebody tell me what is the average of the xi's? I remind you what are the notations. Wi is the wealth of each of the individuals. W is the average over all this wealth. And xi is wi over the average, Now I'm asking you, what is the average of xi? 1. Okay, good. So is there anybody else doesn't know why it is so? Now you explain why.
Because if you add all the wi divided by the average of wi's, then you get 1, because
Okay.
some of them are over 1, some are below. And by average, they need to be exactly the average of w.
Yes. So another way to say it is the following: you take the sum of the xi's, then you get on this. Then you get here the sum of the wi's divided by the average. Now you take the sum of the xi's, and now you divide by their number. This will be equal with the sum of the wi's divided by their number and divided by the average. But the sum of the wi's divided by their number is the average. So you have here the average divided by the average is 1. Okay?
What's xi again?
Xi is this. This is the definition. It's the old wi's, but they are divided by the average of the wi's. So instead of speaking about the wealth of everybody, I'm speaking about wealth divided by the average wealth in that country, which is very logical, because the wealth is in some units. So the fact that he has 1 million when everybody has 1 billion, it means that he's a very poor person. So this xi is a much more natural number to discuss than wi's themselves, which depend on how in which units you are measuring that wealth. And if you are now thinking about xi dynamics, then the dynamics of xi will have a behavior which is very similar with what we had before. Because if I write xi of t plus 1, by definition it's wi over w. But
What
huh?
does xi dynamics mean?
Dynamics means simply what is the law by which I'm getting from t to t plus 1. You see, if I make a picture of this class, then it's a picture, it's statics. That wouldn't tell me very much of what's going on here. If I'm saying, look, there is some law by which what happens, the picture at the time t relates to the picture at t plus 1, then I have the dynamics of this process. Now again, for studying some things in society, maybe this issue of dynamics is not that important. In fact, in economics, most of the technology, most of the techniques are such that they assume that the economy is in equilibrium, and all this issue of dynamics does not appear very explicitly. On the other campus, this is our obsession of describing the time evolution of a system by some laws which allow us to predict what is the situation at t plus 1 as opposed to t. So dynamics, it is again one of the main themes of this course, which is trying to bring the ideas from the other campus here. So now I want to write in the same way in which I had this equation. There is another way to say this. I had these equations in which eta was 1 over m or m with some probability. And knowing this, I was able to predict what is the stationary distribution of the wealth in those conditions in which I was able when eta was going to the left. Now I'm trying to make the same techniques applying to x, because x, while the w's are all of them running to infinity, to larger and larger values, I know that the x's cannot go to larger and larger values. I know that their average has to stay 1. So at least some of them, if some of them are running to the infinity, some of them actually are running to the lower bound. So if I want to find the power law, now I will find the power law in the x's. But since the wi's are proportional at each particular moment, the wi's are proportional to the x's by the average. If I get a power law in the x's, then I will have a power law in w's. So I will have a rather non-trivial situation. It doesn't even happen with people which know a lot of mathematics and know how to play with mathematics, that you start with a process which is not stationary at all. It can do anything according to what the eta I does. Sometimes maybe the average of the eta i's are positive, some of them sometimes is negative. And still I'm going to be able to say a statement about what is the distribution of the wi's at each particular point in time, because I'm able to re-express this complicated non-stationary dynamics in terms of the stationary dynamics of the xi. Is it okay? All this material is on the internet, so it's better if you concentrate on following what I say.
I am, I think I understand.
Okay. No, I'm saying you don't have to take notes. These are the notes. And there is on the internet even little clips with me making the computation by hand.
Yeah, but if I don't write down what a dynamic is, like I won't know.
Okay. So now xi, when I want to write how xi evolves in time, I write xi of t plus 1 is by definition wi of t plus 1 over w, which is the average of t plus 1. But wi of t plus 1 is eta I wt. And w of t plus 1, I leave it like this. But, and now wi of t, I can re-express it in terms of xi as xi times w. Yes? Wi, it's equal to xi times w. So I'm writing in terms of wi, I'm writing xi w. So in the end, what I do have here is that, okay, so this explains exactly what I said, how I got from here to here, and how I got from here to here. So if I only call this combination my new eta, let's call it lambda. It's another random number. It's a complicated random number, but the process now is exactly of the type of this one, except that now I have some complicated lambda I. But now, obviously, I have the lower bound, and obviously, I'm not going to infinity, so I have a lower drift to the left and the lower bound, so I get the power law. And now the question is, what is that power law? Because now it's pretty complicated. You see, the lambda I don't even know what it is. I didn't even tell you what eta I was here. In principle, it could be like in the computations before, 1 over m times 1 over m and m, but I didn't say that. The point is that now I'm back to our old problem, in which, why? Because xi, if wi fulfills this equation, this inequality, that wi is larger than some fraction of the average, xi itself fulfills this, it's larger than c. Is it clear why? You see, wi is larger than c times the average. Yes? Some number. Some
I don't, we have lambda, like there are so many things that I'm not understanding.
Well, there are essentially only three types of numbers here. One are the Wellses. One are the quantity by which you multiply. So it's essentially how much you lose and gain in this process of, let's say, investing in some values. And
huh? And the last is random numbers?
These are random, yes.
The quantity by which you multiply?
Yes. With taken from with some probability, each value taken with some probability, as I described. And there is one more number, indeed c, which describes what is the lower bound. But we even discussed it in terms of intuitive numbers. It is, what is the poverty line? What is the line beyond which you do not allow people to go? Okay? Now, the point is that while in terms of absolute wealth, the wealth is larger than this fraction of the average, if I divide by the average and I speak about the xi itself, xi is just required to be larger than this fraction. It's just another way to say that that the wealth of everybody is not allowed to go beyond a certain fraction of the average. But now it's already, xi is already normalized to the average. So therefore, xi is just not allowed to go below this fraction. This 1 over 4 or 1 over 3.
Why do we put it in a fraction if we have just the number c?
What do you say?
Why does it have to be a fraction?
By fraction, I mean not necessarily that you can put it something divided by something. It's a part of, it's some number less than 1 by which you define the poverty line. If somebody has less than 1/4, it could be a number which is not a fraction, technically speaking. Okay? It's some part of the average.
So it's the lower bound.
This becomes our lower bound. So basically, I'm showing to you that by taking a process in which there are many realizations, and you couple these realizations to one another through this condition that each of them is not allowed to go lower than its partners. Here there is a conceptual jump which is not really trivial. Before that, we had each of the realizations of the process independent from one another. There was a lower bound, which was the same for everybody, but they didn't know. They didn't have to know from one another. They were living in different worlds. They were different realizations of the same process. Here it's a very different, in fact, it took some conceptual jump, which I'm not discussing here because we have many other smaller conceptual jumps which I have to take care of. But this one is indeed non-trivial because you see, now this condition is actually coupling the different random processes. We have now a lot of processes which are coupled by the fact that each of them is knowing about the others through the fact that he is not allowed to go to below a certain fraction of their average. But once I do this change of variables and I speak about the average, about the normalized wealths, then I'm back to the same situation in which I have a multiplicative process and the lower bound, which is fixed. Except that now I don't know what is exactly this lambda. So in order to do that, I'm going to do the following. I'm going to say, okay, so now I'm back to solving a problem which I solved before. What is this problem? This problem is that I have some xi of fact, x, I can think in terms of x because the i's are now just labels. X of t plus 1 equals some lambda, which we could take again 1 over m and m or something like that, x of t. And with x not being allowed, x of t plus 1, not being allowed to be less than some value c. But we know what is the solution of this kind of a problem. Maybe I solved it in a little bit of a particular context. So you'll have to allow me to solve this problem with 1 over m and m, even though I'm not guaranteed. But I will get a situation in which this P of W equals W to the minus alpha, I will be able, I will do, which is again non-trivial, I will be able to compute alpha solely in terms of the of C and M and of C and M, and if necessary K. And in fact, I will get something like alpha equals 1 over 1 minus C in some limit. Okay? So why is it important? Because by doing this transformation from Wi to Xi, I was spoiling a little bit the knowledge about what is my multiplication factor. Now, if I prove that, the exponent alpha of the power law depends only essentially on what I fix to be the lower bound, the coupling between the average and the lower bound, then I'm back in business. I can compute what are my power laws and compare it with the reality and show that indeed, even if I don't make this kind of absurd assumption that people are losing all the time in the stock market and things like that, even if I'm taking a very non-stationary random process, as long as I have a fixed social security bound, C, I have the same power law appearing in that country. That is going to be the result. It's a very important result because essentially that is what was a puzzle for more than 100 years. There was this guy Pareto. He measured the wealth distribution of people in quite a number of countries. He got more or less the same power law. And more or less the same power law, and at least a power law, was true from then on to all the countries in the Western, in the capitalist system for 100 years, even though there were crashes and booms and wars and depressions. So it is important that we get this result in a more general situation by essentially reducing formally to the old system. Okay? You see what I mean?
I don't see how you say that it's the same. The distribution of wealth is the same all over the world, as we obviously know that the Gini. You can see that different countries have different distributions.
Okay, so not only that I agree with you. First of all, it's almost the same. It cannot be too different because the lower bound cannot be too different. Of course, you could have in some countries having maybe 1/5 in place of 1/4, and in some countries, maybe in Norway, it's even it's not 1/3, but even a higher poverty line. And this indeed will influence alpha. So that's and alpha is essentially very similar to the Gini, measures the same thing with the Gini exponent. So alpha indeed changes between countries, but not by very much. And these changes will become apparent exactly in terms of the social security policy of those countries. So in fact, what we are saying is practically interesting. These alpha are characterizing the power law behavior of the richest. And now we find it that it's actually dictated by the way the society, the regulators, are treating the poorest. That's also a very interesting point. So it not only it's a problem, but it's in fact one of the upshots of the entire story. So in order to, okay, I have 1/2 of an hour left. So I'm going to after reducing this problem to our previous problem, I have only this point of connecting the exponent alpha to the lower bound, because now I don't have at my disposal anymore the computation which I did before, because now I don't have a fixed lambda for the W's. I will have a fixed lambda and a fixed bound for the x's. So, but I don't know what it is. So all I know is C. So I have to find alpha in terms of C. And this is what I'm going to do. In order to do that, I need some mathematics, which is high school mathematics. And this is actually the pride of this course, not the actual results, which I could, it's not, most of them are not my results. But the fact that I'm doing this without integrals, without differentials. But what I do need is, for instance, something, this relation. So I'm looking at you because apparently you are the one which, actually I'm very grateful that you are asking me, because in this way I am sure I'm not speaking to the walls. So if I have a number x which is small enough, and I have a number 1 plus x, so it's a number which is just a little bit larger than 1, maybe a little bit lower than 1. And now I want to know what is the power n of it. Okay? Now, what is 1 of plus x to the n? It's 1 over x times 1 over x and so on. Okay? And now, in order to make the multiplication, I can do like this. I multiply the first one here with the first one here with the first one in every one of them. This gives me 1. Then I can take the first one here, the first one here, the first one in everybody except the last one, which I take x. Okay? In order to multiply, I have to take every one of these guys multiplied with everybody else. So one term is it's n, 1. I have another n terms in which I take all the ones in all the other brackets except one of the brackets in which I take x. So there are n of them, as many as the number of brackets. Then I have other terms, for instance, x to the 2, in which I take 2 x's from 2 of the brackets, and all the others are 1s. If I count them, then it comes that they are n times n minus 1 over 2. But I don't have to do this computation, because I'm saying to you the following. You see, I said that x is a very small number. Therefore, x squared is an even more small number. Suppose that x was 0, 0, 1. 100. This is 1 over 10,000. I can neglect it. So I'm going to use the fact that if x is small enough, then 1 plus x to the n is 1 plus nx. Okay? For an n. That's one approximation which I'm going to use. Also, for this kind of sum, I'm using this notation, which please tell me if it is new for you. In place of writing all the time an entire line like this, I put this number sigma for sum. And I'm saying that it's x to the k, where k goes from 0 to n. So it's x to the k, like this k. And in place of writing also x to the 0, x to the 1, x to the 3, I say it's x is the sum of x to the k, where k goes from 0 to n. So this is what I want to compute now. Okay? So how do I compute this? I'm starting with the following identity. This times 1 minus x. I'm going to compute how much it is. And after I do that, then I will be able to take this out from the equality. It's clear what is the plan? Mm-hmm. Okay. So by multiplying this with this means that I multiply 1 with this, which gives me this bracket again. And the second term is minus x times the same thing. Okay? Until now it's clear. Now I'm going to, I'm copying this line, but this one I'm already putting the x into this here. So minus x times 1 is minus x times x is minus x squared, and so on. Up to minus x times n to the x to the n, which is minus xn plus 1. Okay? Now, okay?
Why is it plus 1?
Because it's x times x to the n. It's x to the n plus 1. Okay, so this you have to remember by heart again. X to the, let me put it in a more general a. X to the a times x to the b is equal to x to the a plus b. This you have to remember by heart. So when a is equal to n and b is equal to 1, it's the x to the n times x, it's x to the n plus 1. Okay? Huh? Good. So now, this was the hard part of the computation past, because now all you have to do is to just to have a good pattern recognition and to see that these terms are canceling one another. And what you are left is just with the first one and the last one. So now I can say that this is equal to this divided by this. And this is what I'm doing. So this times this is equal to this, and therefore this is equal to this minus this. But now if x is less than 1 and if n is large enough, then this is for a very small number. And therefore I'm left with just 1 over 1 minus x. Okay? So from now on, in spite of the fact that I said you don't have to remember things by heart, this you should remember by heart. That this kind of sum of x to the k when k goes from 0 to n, when n goes to very large values, to infinity, and x is less than 1, it's essentially 1 over 1 minus x. Good. So with this, I'm going to return to our problem. I reduced the previous problem of wi to the problem of xi. And I said that if xi, for instance, fulfills a random number multiplicative process, let's say of the same type that we have solved already, then the probability of, except that now the lower bound is not at 1, but at c. So if I start, let's say, with everybody at c, then the only allowed values are c, c times m to the 1, c times m to the 2, and so on. Yes? And the probabilities, as you remember, were proportional to m to the minus n and some power alpha. But now I want to work with but now I want to work with probabilities, and because of this, I want to know what is this constant, which will allow me to have a situation in which the sum for all the n's of these numbers will be 1. Okay. Until now, I said, okay, what is the relative frequency of xi equal to c to xi equals to c times m. Now I don't want only the relative frequencies. I want the probabilities. So in order to do that, I have to divide by the entire sum of everybody. So I'm saying that the sum of all these things, which is this sum, has to be equal to 1. Okay? Are you following what I'm doing? I know what is the frequency, so to speak. I know that the relative numbers of guys which have c and c times m and c times m to the squared is given by these factors. But I want now to know exactly what fraction. Again, fraction not in the sense of something divided by something, but what part of the entire population is. Huh?
What percentage?
Yeah, percentage. Thank you. Okay. So in order to do that, I say the sum has to be equal to 1. Therefore, this entire sum here has to be equal to 1. The constant, of course, goes outside. And I have the sum of m to the minus alpha to the n. But if I call m to the minus alpha x, then this entire sum is equal to 1 over 1 minus x. Because this is yeah. Yes? Suppose that m to the minus alpha is x. I don't want to write on this beginning. This is x. And this sum, forget the constant now. The constant goes outside the sum, of course. If I call this x, sigma of n, sum x to the n, we computed it. We know what it is. It's 1 over 1 minus x. And since x is m to the minus alpha, it's 1 over 1 minus m to the minus alpha. Yes? Yes? Okay, good. But this has to be equal to 1, and this fixes the constant. From now on, I work with probabilities. Probability that one of the x's will be equal to c to some times m to some value n. It's equal to this normalization factor, this constant, times m to the minus n minus alpha. Like before. The only thing is this green thing here. It's not very important, but I'm trying now to extract very exact things. So I need real probabilities. For instance, why do I need probabilities? Because I want to exploit the fact that I know that the average of xi is equal to 1. You remember, we established. Now, what is the average of a number? It is the sum of all the values which this number can take, each of them with the probability of that value. Are you aware of it? What is the average of some quantity? Suppose that I have a quantity which can take value 1 with probability 1/3, 2 with probability 1/4, and 3 with probability what is left after I subtract from 1, 1/3, and 1/4. How do I compute the average? I multiply 1 by 1, what did I say, 1/4? 1 times 1/4 plus 2 times 1/3 times 3 plus 3 times 1 minus 1/4 and 1/3 is something like probably 5 over 12 or something like that. Doesn't matter. The matter is that I take the values which are allowed for xi, and each value I multiply by its probability, and I make the sum over them. And this is the average. Yes? So on one hand, I know that the average is 1. On the other hand, I have this formula which connects this entire story here with 1. So, but p. So now I have to put in place of p, I put what I know that it's the value. This is why I computed p, the probability, so that I can put it here. So it's the sum over, again, I'm copying the value c to the m to the n, times the probability of x being c to the c times m to the n, which is this. I just substituted. Okay? And now you see that I have a good chance of getting rid of the alpha. Now the point, you remember, I just wanted to know what are this power law and to fix alpha. And now I have a chance to fix alpha because I know that this entire thing is equal to 1. And this is an expression which contains m, c, and alpha. And of course n, but it's summed over n. So there is a very good chance that I will be able to write this power law only in terms of what is my poverty line. In terms of economics, since we already discussed it, might help to understand. It's saying, given the poverty line, I'm going to tell you what is the exponent of the Pareto law. That is what I'm going to do, which is important because one thing is to make some mathematical computations here in which I might even make mistakes and you would not probably even catch me. And another thing is to come with a very precise prediction saying, look, people, if you have this particular poverty line in a society, I'm telling you what is going to be the Pareto distribution of wealth. And not only that, in the future lecture, I'm going also to tell you what is the kind of fractal fluctuations which the market is going to have in such a society. And even show that if you have too much inequality, then the fluctuations in the market are going to be unsustainable. But now I'm just making, actually I have enough time to, the entire computation looks complicated, but it's only one slide. In the moment that I'm getting here, we'll have the result. So because of this, we have plenty of time. You just ask me whether there is any problem. So again, I have the average of x, I know it's 1. On the other hand, there is another way to write the average of x as the values which x can take times the probabilities of these values to appear. And I substituted the probabilities here. And now, look what happens. This doesn't depend on n. This is a sum over n. So you are aware that if I have a factor here which does not depend on n, I can take it outside the sum. This is a sum distributivity. So this factor here, the green one, and c, both of them don't depend on n. I take them outside the sum. Of course, these ones, I cannot take them out of the sum because they do depend on n. So I have this entire sum is this equal now to this factors times this sum. This sum, again, I'm using this thing which I ask you to remember by heart, that m to some power times m to some other power is the sum of the two powers. So this sum here is m to the power n times 1 minus alpha. Not only that I put n minus n alpha, I also took n outside, and I have n to the power 1 minus alpha. Now you see that mathematics is very merciful with us, because this thing looks very complicated, but we are returning back to the only formula which we know by heart, which is the sum of some x to the power n. Because m to the 1 minus alpha, I can call it x.
You can call anything x. Why are you calling that specific thing x?
Well, I can call it anything x, and indeed, if I have that x to the power n and sum over all the n's, then I know what is the sum. The point is not calling it x. The point is that, as you see here in this jump, in the moment that I call it x and I have this sum over n of something to the power n, I know what is the answer. I just did it on the slide before. You remember that. You even accepted what is the, now you cannot go back. This thing is equal to 1 over 1 minus m to the power 1 minus alpha. This is my x here.
Why are you calling it x?
Because I'm betting on the fact that you remember this formula which was true for x.
Okay, so you just mean you use the same formula.
I'm using the same formula. I call it x, and I catch you on your word that you accepted that the sum of something to the power k with k between 0 and n, when n goes to infinity, it's equal to this.
So when you're saying we're calling it x, you just mean we're doing the same to it
Yes.
as we did in
Yes,
the previous
you see,
example with the
people,
x.
exactly. You see, unfortunately, even when it comes to mathematics, a lot of things are jargon. Like the story with the fraction. If I will only set the percentage, then you wouldn't get confused. Okay, so I call this x, and the entire sum, the entire, when we were at this stage, you for sure, not only you, even I, if I would be in an audience, I would say, gee, this is going to be a terribly complicated thing. And out of a sudden, you see, it's a very simple thing. 1 is equal to all this, which means that m to the alpha, which was here problematic because I didn't know what is alpha, and therefore I don't know what is m to the alpha, I can now essentially get m to the alpha from this equation that 1 is equal to that. So there are two ways to take it from here. One way is to write. I'm sorry. Ignore for a second these 3 lines. Okay. I'm still at this point, and I'm saying that this is equal to 1. Therefore, this times this, it's equal to this. Because it was divided by this, 1 is equal to this divided by this. Then this is equal to this. If something divided by something is equal to 1, that it means that they are equal. And this is what I'm writing here. C times minus 1 m to the minus alpha is equal to 1 minus m to the 1 minus alpha. Okay? Which means that m to the minus alpha, when I'm, it's equal to 1 minus, this you cannot see immediately, but you can, if you want, you can believe me. If not, I'm making it. It's clear that I can extract m minus alpha from, as a function of m and c. Yes? And it's equal to that. It's 1 minus c divided by m minus c. That's it. Now I can put it back there. Remember that C is actually W minimum over W average. And now I have that the probability of Wi over W mean being C to the M to the N is equal to this formula, which looks complicated, but it's after all just one normalization factor and something which doesn't matter how I call it, but it's to the power n. It's a power law, and it's computable by just knowing what is the ratio between the poverty line and the average wealth. So I can go now, if I measure the average between the if I measure the average, the ratio between the poverty line and the average wealth, then I can now make a prediction about what is the power law which is respected by the wealth distribution of people, even if they are much richer than the poverty line, especially if they are much richer than the poverty line. Still, this formula is a little bit complicated, even for me. So I'm going to do it much simpler. In the end, it will be such a formula that you are allowed to, you are not only allowed, but even capable of remembering by heart. I am capable of it. So let's see, how do I do? I have here m to the minus alpha, okay? But let's suppose that, which is in fact the case, you see I took m discrete, like 2 multiplying by 2 or by some other value, because I wanted to have this discrete sums and being able to make all these tricks without integrals. But in principle, of course, the wealth, when somebody gains, it doesn't gain by a factor of 2. It can gain, typically it gains by a factor of 1.1 or something like that. Therefore, m, I take m like 1 plus y, where y is a small number. Y is how much I more or less I expect to gain in one day. Of course, if you put the money in the bank in Israel, then you really get a very small y, because it's less than 0.5% per year, not only per day. So y is a very small number. Okay. So when I have here m to the minus alpha, I can apply what I said, that 1 plus a small number to some power is just 1 of that number multiplied by that power. Remember? I call minus alpha n. Now you know what I mean that when I say that I call minus alpha n. That I've proved the formula for 1 plus y is equal to 1 plus ny. And now if it is at the minus alpha, it's 1 minus alpha y. And I remind you how we did it. Well, so here I will have 1 minus alpha y in place of m to the minus alpha. Yes? Where y, it's this quantity which characterizes m, by how much I multiply or I subtract when I make my little steps of multiplicative random walk. And now I have 1 minus m to the 1 minus alpha. Now I call 1 minus alpha n. Okay? I'm allowed. And now when I divide by 1 minus. And now in place of m to the 1 minus alpha, I put 1 plus y times 1 minus alpha. 1 minus alpha is n. It's my n. And therefore, it's in place of 1 plus y to the power 1 minus alpha, I just write 1 plus 1 minus alpha y. Okay? Now look what happens. 1 with 1 goes, 1 with 1 goes, and I have here c times alpha over 1 minus alpha. Now I'm really in business. Because now I have that, don't forget, this entire story is equal to 1. So I have C alpha over 1 minus alpha is equal to 1. Now it's not difficult to compute alpha as a function of C. And one way to do that, pay attention, because it's, from time to time I really do things in the head, and I try very much to not to jump. So what I will do it on the board. So I have 1 equals C alpha C alpha over 1 minus alpha. This means that I can bring it here with 1 minus alpha over alpha equals to C. I just multiplied by 1 minus alpha over alpha, and I cancel this, and I put, and it appears on the other member. And this is 1 over alpha minus 1 equals C. Yes, because I divided. And this is 1 over alpha equals, I'm sorry. There is a minus someplace. It's plus alpha here, because there is a this is a minus with minus, and this is alpha minus 1. It's a mistake. It's alpha minus 1 because there is a minus here. It's minus. This one with this one goes, but here I have minus 1, and minus times minus alpha is plus alpha. So it's good that I did it by hand because it's a mistake there. So this is alpha minus 1. This is alpha minus 1. Therefore, this is minus 1 over alpha plus 1. So minus 1 over alpha is minus 1 plus C. And therefore, alpha it's equal to 1 over 1 minus C. Again, I jumped a little bit between these answers, but this you can see. Yeah? Great. So look, this result, maybe I obtained it with very modest mathematical sophistication, but it's a tremendous realization in a sense, because we are speaking now not about some hypothetical idiotic economy in which everybody loses, and therefore you have a lower bound, and therefore you get some prediction about obtaining power laws. Now we are speaking about a very realistic situation in which you have a pretty random fluctuations in the way the entire economy goes, because I didn't put any conditions on the multiplicative factor. And you get that you do get a power law, and that power law depends only on one thing, on where sits your poverty line. So, so I finished exactly in time. This is a very nice place to stop. Thank you.